Yeah, so good afternoon from India. This topic is related to the study of neutron stars in the section of general theory of relativity. So, first of all, this is the outline of my talk. We will start with the background of the general relativity and then how anisotropy came into picture, and then some specific geometry that we are going to consider here, that is Tolman-Kuchowicz. And then we will see that how quadratic equation of state plays a vital role here in studying the anisotropic fluid distribution. And then we try to construct a mathematical model which basically well behaves, and it will be having some criterion satisfaction so that we can see that it basically matches with the observed data and pulsars as well. So, and the obviously the pulsar of interest here is PSR J0952 So, basically, this is one of the recent pulsar that has been observed with greater mass. So, the first phase of my talk is the basics of life cycle of a star that we are already familiar with. So, I'm not going into the details of each and every phase, but you have a clear picture here that basically demonstrates that if you start from the nebula here, for example, this one. So this part is nebula. And from here, these are various stages that this dust basically comes into picture. Basically, it will be now then giving us dust cloud, and then from that cloud, you will have a globular structure, and then the first protostar will be there, and then there will be a brown dwarf, and then main sequence star, something like that. So this whole cycle basically predicts us that what are the fates of the star. Okay, depending upon the matter distribution which is there in the star. Okay, we will come to the conclusion that what will be the fate of this star. And eventually, as we know that now black hole is very well detected, and we have seen the outcomes of that on the basis of gravitational waves. So finally, black hole is also a fate of star with very high gravity. Okay. Now, my research interest based upon this all fate of stars, if you see, that comes or fall down to this neutron star. So this neutron star is really an interesting object, which basically lies between this other fates and the black hole. Okay, so it's closest neighbor to the black hole, and they are very dense and with a very high gravity because of that. So when the early formation starts, we are having this kind of region, and then scientists they are studying the hydrostatic equilibrium, which is responsible for the stability of the star, and eventually it also turns out that there is a connection between the star's shape as well. For example, some spherical structure or maybe some non-uniform star. So hypothetically, that was there in scientists' mind, but practically speaking, in 1972, at that time, Ruderman and Canuto, they both have studied this, and they proposed the theory that there must be some anisotropy here, which basically may give you a deformed structure of the star than the usual one. Okay, so now before we go into the depth of that theory, these are some statistical values of different states of the stars. For example, if we are dealing with white dwarf star, then basically it has a very low solar mass, that is 0.17 solar mass. And majorly, if you observe any white dwarf, it basically lies in between this range, zero point 0.5 to zero point 0.7. The color will be whitish or bluish color, and it has some spectrum which is ranging from O, B, or A type. And then the temperature is, when you see in kelvins, it has 0 degree Kelvin, almost cold star, and there is no fusion process going on. And 4,300 kilometers with solar mass, that is the diameter of that star, and the surface gravity as well. The red dwarf, again, these are dwarf stars, as you can see, and hence they are having a lower solar mass along with some special peculiar properties. Similarly, for brown dwarf, you can see here violet color structure, and they are having very low visible light here. So they are not having, that much intense emission of radiation. And next is the main candidate of our research study, that is neutron star. As you can see here, they have higher solar mass, 1.4, and their temperature is 1 million Kelvin almost. Yeah. So, and the size is very small. You can see here the diameter or the radius is near to say 7 or 8 kilometers. So yeah, diameter is 10 to 15 kilometers, and hence this is a very very dense structure. Okay, it is made up of neutrons. Obviously, that's why the name is there. And then you can think that this is the next state after a supernova explosion. Yeah. So this is obviously different than the previous stars that we have seen. And that was the reason, that is basically the reason why scientists are getting more involved, because this is having a very superpower, and hence we basically are not knowing much about these stars, these kind of stars. Yeah. So, how do we study such kind of super dense stars? And for that, there are several theories and propositions were there. Among that, if you see here in the last topic here, that is this MIT-Wake model. This was one of the popular model at that time. It was proposed in 1975. So basically, what they are trying to see here is that what could be the inner particles of these neutron stars? Apart from neutrons, what are the other exotic matter that we are not aware of? Such kind of situations are there everywhere. And hence, they are trying to find that what could be this internal matter. And there are several theories which basically tries to resolve this mystery. And among those things, since Einstein was there and he proposed the general theory of relativity, that was the first key step helping here in order to understand this situation. So, what was that? Basically, he gave us field equations, which basically gives us an idea in simple language about density, pressure, okay? And we know that when density and pressure is known, we can think of equation of state. So there are many options here that what can you, whether can we predict here about density structure, or maybe what will be the internal pressure here. If we can predict those things, then definitely we can think of what are the causing particles here, which basically gives us this much dense situation, or maybe the tremendous pressure. Yeah. So for that reason, these are the key or fundamental equations, and basically it represents the curvature of space-time and how it is related with matter. So these are the field equation, okay, and they are basically gives us the relation. It comes from the tensor calculus, and here these equations basically give us the relationship between this matter and energy, and hence energy momentum tensor comes into picture. And again, for several stages, we will have this kind of situation. So for dust particle, you will have energy momentum tensor in this way. T mu nu is equal to rho u mu and u nu. And for perfect fluid distribution, we can have this one. And this is a widely popular and used equation. So for perfect fluid, and then if you want to go with even anisotropy, then also it is possible. Now, before we dwell into those equations, let us try to understand what do we mean by anisotropy. You can think of like this, that if you are having a sphere and it is a balanced sphere, that means the internal pressure and the outer pressure, basically they are counterbalancing each other. And hence we have uniformity. So to preserve this uniformity, we should have that balance forever. And this kind of situation where you are having that uniformity, that is called isotropy. But Anisotropy, that means this balance basically collapses. So when internal pressure or outer pressure, they are not equal in the amount, then definitely there must be some deformation is there. So that deformation depends upon whether radial pressure is higher or maybe the transverse pressure is higher. But based upon this situation, anisotropy will occur. And that was the first thing that I told earlier, that in 1972, this thing was proposed that, yeah, anisotropy must be there in neutron stars because of a very high pressure. And as you can see, that the temperature is in millions of Kelvin, and at the same time, the size is very small. And hence, the internal pressure and the density, the gravity is very, very, very strong. As you can see, that even a spoonful of amount of the matter from neutron star weighs tons of thousands of kgs, and hence anisotropy must be there. That was the first proposition, and hence the natural equation is nothing but a difference between these two pressures, transverse pressure and radial pressure. So that part basically added here in the isotropies equation. So when we just want to study isotropy, then energy momentum tensor will be this one. But if you want to study the anisotropy part as well, so that counterpart can be just on the basis of, can be studied on the basis of the addition of this additional term. The first proposed theoretical model to study this anisotropic matter distribution was proposed by Maharaj and Martens in 1989. And then they studied this and they developed an algorithm that if we want to study the anisotropic matter distribution, then what will be the governing energy momentum tensor? So this is the governing energy momentum tensor equation, where obviously rho is the proper density, P is the isotropic pressure, and Ui is the pore velocity field of the fluid. Now, this is the basic representation. But what do we mean by this pi ij? This pi ij is basically, if you can work it out, then you will be having this expression, root 3 times s, and then in bracket, this one, where the ci is nothing but a radial vector representation. So this expression they developed in the 1989 paper, and then they proposed that basically pi ij can be replaced with this vector, and hence we can now smoothly introduce anisotropy in our study. Now, furthermore, they have computed each and every components which were involved in energy momentum tensor. And obviously, these are the pivotal elements, T00, T11, T22, T33. And they solved these equations and they came up with this conclusion that these are the primary components of energy momentum tensor. Rest of the components were vanishing. So these are only non-vanishing energy momentum tensor components. The radial and transverse pressure, if you can compute, then it will be in this form. And finally, this S, which is called as anisotropic parameter, okay, or magnitude of anisotropy, that can be related with PR minus P per upon root 3. So basically what we have done, we started with the fundamental equations. We wrote down energy momentum tensor. And obviously, tensor was consisting of 16 components. But if we try to solve all these components and try to find out the non-zero values, then these are the non-zero or non-trivial values. And based upon that, we could also find the relation between PR and P per. And then we could establish the proper anisotropy factor given by this expression. S is equal to PR minus P per upon root 3. Now, this was the fundamental workout that we are going to use in our study, in our mathematical model. So the primary thing is, since we have this kind of situations, I mean, what kind of situations where we are directly thinking of anisotropy, then these are the things. If you see the solid core or a type 3A superfluid, then also you can think of anisotropy. Then various types of phase transition occurs. At that time also, anisotropy might be there. If you think of pion condensation or slow rotation is there, or maybe a strong magnetic field's presence is there, or maybe a mixture of two different kinds of fluids. In such situations, definitely anisotropy dwells there. And this was proposed in 1972 by Ruderman and other scientists. Yeah, so this was the primary confirmation that we are going to study some legitimate thing and not only a hypothetical thing. Once it is established, along with that Maharaj and Martin's algorithm, we are having a very strong setup of field equations. Let's once again recall the thing. Einstein gave field equations in general theory of relativity. What are those equations? Basically, they gave us a picture that how matter and energy they are related with each other. Based upon that, curvature is there, and then we are trying to see the basic physics or geometry of a given metric, seed metric. And based upon that, several scientists, they have worked out a very steady solutions. And out of those persons, one person got basically he got succeeded, and that is called Schwarzschild. So Schwarzschild has developed a final stable solution for that. And then that metric is also called after his name, that is Schwarzschild metric. He gave us an exterior metric, and also he developed interior metric. So what is exterior metric? So if you consider a matter distribution, then outside the vector matter distribution, there is a vacuum space there. So if you think of that, what will be the state of this matter in vacuum, that can be studied on the basis of Schwarzschild exterior metric. And what will be the interior of this matter distribution, that can be studied on the basis of Schwarzschild interior metric. Now, these are, already a stable solution for us. We can basically try to work out in this way that since it is a standard model, Schwarzschild exterior metric, if I'm assuming some new geometry for my matter distribution, which involves anisotropy, then let us try to connect these two things. So this is the exterior part, this is interior part. I will try to generate interior part and try to smoothly match with exterior. And if without any hassle, without any any other situations where they are not matching, if without any frustration, if I'm getting the exact matching, it means my interior model is basically a well-connected solution with the exterior one. And hence, there is no discrepancy, and I can assume, I can guarantee that this model is stable. That means whatever I have constructed mathematically, that basically also connects physically. Okay, it basically satisfies these requirements. And hence, why and how we can connect this with the real world problem? We can also predict the radial pressure, transverse pressure, or density distributions, and other several factors are there, which we can predict on the basis of this mathematical model which we have developed. And based upon that prediction, we can directly connect with the observed pulsars. And if we are finding the similar kind of situation, that this will be the density or this will be the pressure, then we are through. We have achieved that level that if some other unknown pulsar is there, we can directly implement our model, and we can also predict the matter content, their distribution parameters as well. So basically, this is the outcome, and this was the reason why such kind of studies are widely popular and important. Coming back to this one, so here, these are three key equations for us. And as you can see here on the left-hand side, these e to the power minus lambda, or maybe e to the power mu, if you want the role of mu, that is basically coming from this one. Yeah, this is the seed metric. It is known as a seed metric. And if you try to solve this equation on the basis of this energy momentum tensor assumption, and of course, now there is an involvement of anisotropy, and hence we have this setup of these three equations. And once we have those equations, we can think of the possible variations as well. For example, if I'm dealing with those equations, that is related to the uncharged matter distribution. But what if the star is having some magnetic field, or maybe some charged matter is there? If electric charge is present there, we need to incorporate that content as well. We need to incorporate that term as well. And for that reason, this is the electromagnetic field that we can introduce here. So the matter distribution, which is isotropic, that can be easily studied. the matter distribution, which is anisotropic, that also can be easily studied, and the matter distribution, which is having some charge is there, then also it can be studied because we have now well-defined equations. And those are coming out from, obviously, the Einstein-Maxwell field equations. So these equations basically give us the value of, the behavior of the charge as well. Okay, you can see here some extra terms containing this Q that is basically related to charge. So we have a very simple connection here with isotropy, with anisotropy, and with charged matter. As I told earlier, that Schwarzschild gave us a very nice solution that is related to the exterior metric. So this Schwarzschild exterior metric represented here, and this is the mass and radius of the matter distribution that we are thinking of. And again, there is no electric field here, but if you want to uh, take into picture this electric field, that is the charged matter, then there is another metric called Risner-Nordstrom metric that we need to consider. So let me here give you a brief idea. Equation number 7 that can be used with the matter distribution which is having no electric field. Okay, so at that time, Schwarzschild exterior metric should be matched with the interior metric that we have generated. Okay, how we will generate? After a couple of minutes, I will come back to that topic as well. But once we have generated that internal solution, that should match smoothly with Schwarzschild exterior metric. And if I'm thinking of considering of charged matter distribution, I need to have connection with Risner-Nordstrom metric, okay, which is equation number 8. So if they are basically at a boundary, if they are smoothly matching with each other, that means there is no flow, there is no miscalculation in our mathematical model. We are good to go. Now, once we have this one, as we know that there is matter, density and pressure, they are related with equation of state. So what kind of equation of states are there? Basically, in literature, if you go with a variety of equation of states, then you can list out those things. The first one is a linear equation of state. As you can see here, this radial pressure is connected with density in linear way, alpha rho minus beta or maybe plus beta, whatever we consider. But that is the linear equation of state. Another one is MIT Bag model. That is obviously, name itself suggests that it has been studied by Massachusetts Institute of Technology. So that is another one where they talk about gluons and quarks in the matter. They consider basically this matter distribution in terms of sphere, where quarks and gluons are there inside the sphere, and they give this structure the name called bag. So in that way, that name occurred here. Similarly, a quadratic equation of state, then color-flavored locked EOS, then polytropic EOS, Chaplygin gas model, and then van der Waals equation of state. So these are variety of equation of states that comes into picture while studying the stellar structure. So we have numerous possibilities. We can have many variety of metrics which can be thought of as an internal metric, which provides basically an interior metric and the matching with the suitable exterior metric. So we have requirement of those interior metrics along with the assumption of such kind of equation of state. So either you choose the equation of state or maybe you choose some different central pressure. And what is the reason of this assumption? Because we have a few equations and more unknowns. So basically 4 unknowns and 3 equations. Obviously, one condition needs to be assumed here. And that's why we are assuming the pressure relationship. And that's why that EOS come into picture. That is the basic idea or gist. Okay. Coming to the next part, once we have constructed a mathematical model, we have checked that what will be the suitable condition for testing either Schwarzschild exterior metric or Risner-Nordstrom metric. Then we come to this part where we are having some primary criteria, whether we are going in a right direction or not. Okay, that basically depends upon these conditions. So metric potentials, when you consider a metric potential, e to the power lambda or e to the power nu, they must be non-negative in the range 0 to a. Now, what is a here? It is basically in simple language, it is nothing but a star's radius. Okay, and r is the radial variable. So when radial variable from the center to the surface, when we consider the full range, it becomes the range 0 to a, small a. So in this range, if you think, if you see, then your metric potential should have this non-negativity. That is the primary assumption. Second one is your density, your radial pressure, or transverse pressure. Whatever the expressions we have found, it should be throughout non-negative in the range 0 to a. Okay, so density, radial pressure, tangential pressure, they should be non-negative as well. The third condition is your radial pressure should be 0 at boundary. Okay, the fourth condition is causality condition. This is basically related to the sound speed as well, and it should be lying in between 0 to 1. Yeah. So dp r by d rho or dp per by d. Yeah. So if this condition meets, then we are halfway, we have completed it. And then some energy conditions to be checked here. Again, these are different relationships. Once you have the expression for rho, once you have the expression for PR and P per, you can quickly cross-check these values, okay, from the, from inside to the outside, that is the whole region. So if these all conditions are satisfied, these five energy conditions and the previous conditions as well, causality conditions, and further more conditions are there which are required. The first one is monotonic condition, then mass radius relation, it should satisfy this one. Surface redshift can be obtained with this expression, and gravitational redshift of the stellar configuration. So these are well-defined calculations, and these are primarily requirement for the stability of our structure, that these conditions must satisfy. Otherwise, whatever we have done in our calculation, that is primarily wrong. It won't give us any physical backbone. Yeah, and then even we need to have a stability of three different forces: gravitational force, that is called as Fg; hydrostatic force, that is Fh; and anisotropic force, Fa. Okay, this condition should match basically, and then based upon that, this equation number 11, this is important: Fg plus Fh plus Fa, it should be 0. Not only that, adiabatic index is also primarily required here for the stability of our mathematical structure, the model, and that can be obtained by rho plus PR upon PR, dPr by d rho. Now, basically, this gamma is nothing but an adiabatic index, and is posed by Chandrasekhar. Basically, adiabatic index must be greater than 4 by 3. So, if whatever the expressions we have obtained, if we substitute all these values here and simplify it, and if we find that gamma is less than 4 by 3, then our mathematical model is not acceptable. Okay, physically it is not stable stellar model, and hence it will be immediately rejected. Similarly, the Herrera condition for stability, okay, and potentially stable region is -1 to 0 when this difference is there. And when is this difference is in between 0 to 1, then it is potentially unstable. But overall, if you see, then this modulus value should be lying in between -1 to +1. So if it crosses beyond that, then definitely one of the conditions will not met for the acceptability of our model. So again, in that case, we have failed. Now, this was the primary logic, of the whole theory and connections and requirement. So once we have understood that, now let's quickly go to the actual part or the main part on which we have studied. So we started with the static spherically symmetric space-time metric, which is given by this one. And here, generalized Tolman-Kuchowicz metric is given by these two expressions. You can see here and correlate this thing. E to the power nu is also there. E to the power lambda is also there. So we have seed metric, and we have made this assumption. Tolman-Kuchowicz is very well established metric out of many several metrics, and we started with that one. That what if we consider this metric along with the quadratic equation of state, whether we are going to whether we are able to get the stable solution or not. That was our primary concept. So we started with Tolman-Kuchowicz metric along with the quadratic equation of state. And then, based upon our workout, our idea, what we have thought is let us try to implement this on the heaviest well-measured neutron stars in recent days. Okay, so this star, this pulsar, PSR J0952 it is basically the one of the largest pulsars, I mean heaviest pulsars, and let us implement our theory, the mathematical model, whether it basically satisfies this star or not. So we were also curious, and then we started with the again anisotropic solution as our fundamental equations. And when we tried to derive those equations on the basis of Kuchowicz metric, what we have found is this density equation. This was our radial pressure. Of course, even radial pressure was turning to be a heavy equation. Otherwise, what usually happens is radial pressure is having a small expression. I mean, it is not having that much large calculation, but still, you can see here the intensity of the equation. It is having larger terms. And of course, that will reflect here in calculation of anisotropy as well. So this delta is nothing but an anisotropy. And we calculated this anisotropy expression and P perp expression. And finally, we found out very interesting results. As you can see here, these all requirements that we discussed earlier, okay, those were really satisfied, I mean, in a very positive way. As you can see here in figure 1, density. So, I mean, density graph is there. And you can see here, it is in terms of MeV per Fermi cube. Usually stars, I mean neutron stars, they are having the density in terms of 1400 or 1500, sometimes 1700 with charge distribution that we studied in past in 2014 also. But then when we discussed this star, basically the highest or heaviest pulsar, you can see here that how this range grew up. When you see 2.38, that is this heaviest pulsar, and you see here is these values for different values of power, you basically reach up to the highest density. One of the highest densities, 2500 MeV per Fermi cube. Yeah. So in the same way, obviously radial pressure and transverse pressures, they are also very satisfying. They are giving very satisfying result. And then tangential pressure. Okay, now what are the insights of these graphs? Basically, the primary requirement that mathematically that was there, that for example, this one, this range must be satisfied 0 to 1. And you can see here in this graph that it is lying in between 0 to, in fact, 0 to zero point 0.2 only, or maybe here zero point 0.4, not more than that. So basically, it satisfies that range. That was the primary requirement. And we eventually obtained that one. As I already told, the adiabatics index that should be greater than 4 by 3. And you can see here in this figure that is clearly greater than 4 by 3. Okay, it is near to 2. And hence, these equations are also, I mean, these conditions are also satisfied. Not only that, these are energy conditions, okay, weak energy condition, null energy conditions, okay. And these conditions are also very well satisfied. In fact, FG, FH, and FA, these forces we also calculated and we obtained 0 as well. You can see here, this nullifies each other. So basically, these all graphs are well behaved, and that gives us an insight that we are getting some fruitful solution on the basis of the assumption of Tolman-Kuchowicz metric and this mass function along with radius and other graphs. And finally, we also imposed here Harrison-Zeldovich-Novikov criterion. So basically, this gives us the mass function relationship and its nature with the density. And that graph is also well satisfied. So with this, we have found a very mathematically stable stellar solution, which basically satisfies all the primary requirements. And it also gives us an insight that what could be the maximum possible density or radial pressure of that heavy pulsar. So we could connect our theoretical work or mathematical model with the physical model as well, the realistic pulsar, with which we tried to connect this thing and we could match the observational data. So with this, I'm finishing my talk. Thank you very much.
Thank you, DISHANT. Well, yeah, neutron stars are very different from planets and so on. But I've always, in your work, you've always looked at the physical conditions and the physical feasibility of mathematical models and match it to measured data. That's always very important. Are there questions from the audience? I see some applause.
Thank you.
Fidel, please. Fidel.
Hello, can you hear me?
Yes.
Yes.
I have a question, maybe one remark.
Yes, sir.
If it is possible, you can present page 18, 18, your presentation, page 18, please show.
Page 18, okay. Just a minute, sir.
Hello, Richard.
Hello, Johan.
Page 18.
Yes. 18. So,
yes, sir.
Okay, so I have only, this is no question, rather a remark. So this
Yes, sir.
metric form presented in the third line is very important, described very important class of spacetimes. And I can say that such metrics satisfy precisely Ricci tensor, Carvacci tensor, and Y-conformal Carvacci tensor satisfy some conditions, Carvacci conditions, call it pseudosymmetry type conditions. This is only a
yes, sir.
Yes.
Thank you, sir. Yes.
Okay, thanks.
Yeah, DISHANT, it would be good to look at the work of Richard on pseudosymmetry.
And of course, related to joint work with Professor Verstralen and his co-workers. And also I can say that Afsos Ali Sheikh from India also in his team worked on this investigation of